Let me start by recapitulating what I did in the first lecture and what did we learn. So, we learned the basic approach of kinetic theory. So, what is our purpose? Purpose is to understand the thermal properties of matter and connecting to the corresponding equation of state. Okay. What do we mean by equation of state? I told you, let us take an ideal gas. Okay. The equation of state for n mole of ideal gas is equal to PV is equal to nRT. So, n mole of ideal gas satisfy this equation of state. Okay. Now, we are dealing with so called chemical systems. A chemical system is described by the variable pressure, volume and temperature. There could be something called chemical potential which is actually beyond our limit. We will not get into what is called chemical potential. So, I told you in the very beginning that I am taking the first approach to study the thermal properties of matter. That approach is called kinetic theory approach. In the kinetic theory approach, we consider molecules. If I do not mention otherwise, I will be dealing with monoatomic system of molecules and I analyze the motion of these molecules inside a container to connect to the so called equation of state which I have written for an ideal gas PV is equal to nRT. Now, question is, which I tried to emphasize many times in the last class, that this system has a huge number of particles. I have 10 to the power 23 particles. They are identical particles, I am assuming for the time being, but these particles are huge in number of the order of 10 to the power 23. All of them satisfies classical Newton's equation of motion. Now, question is, how do I handle so many second order differential equations? I cannot do that. Here comes the concept of average. Okay? Here comes the concept of average, where I will be talking about average distribution. I will talk about average velocity. Okay? Now, to emphasize what do I mean by average, I have to bring in the concept of distribution function. Okay? I have to bring in the concept of distribution function and probability. So, that is where we are deviating from our well known world of Newton's laws. Here I am bringing in the concept of probability. This is where I gave you the example of dice. If we have a completely unbiased dice, then I know for sure that I throw the dice. With probability 1/6, I get one of the 6 possible values. But what we will be interested in is a continuous variable. Okay? Let us say continuous variable which is x. Okay? This can take any value, let us say idealized situation, from minus infinity to plus infinity. Okay? And there is a probability distribution which I can draw for you. For example, Px as a function of x, x ranging from minus infinity to plus infinity, it takes some value like this, let us say. So, now it is not meaningful if I ask you what is the value of x. Rather, I can ask you the question, what is the average value of x? What does this curve signify for us? This is x. If I call this x plus dx, okay, then this gives me the probability, okay, this gives me the probability that my variable, the random variable I am considering, lies between x to x plus dx, okay, lies between x to x plus dx, and there are conditions which I imposed. Firstly, normalization, which tells me that total probability Px dx is equal to identity. Okay? So, recall the example of dice, it has 6 phases, each number comes with a probability 1/6, but total probability is 1/6 into 6th, okay, 1/6 into 6, which gives me identity. Okay. The same thing is written in mathematics. Now, you can ask me what is the average value of x? That average value of x will be given by again integrating from minus infinity to plus infinity x Px dx. Note, Px dx is the probability x lies between x to x plus dx and corresponding value is x. So, I integrate, I get the average value. Now, in kinetic theory, we will be encountering situation like this. I cannot talk about the velocity of a molecule, rather I can talk about the velocity distribution. This is beyond us, but let me just for the sake of completeness tell you that probability distribution of, let us say, x component of velocity. As I considered in the first lecture, probability P Vx dVx is probability that the velocity, x component of velocity to be precise, lies between Vx to Vx plus dVx. This is the probability, and as I emphasized in the first lecture, there is no difference between Vx, Vy and Vz. This is the isotropy. Density is same everywhere if you like, that is called homogeneity. So, Pvx dx usually is of the form alpha Vx square dVx. Okay? It is proportional to dVx and there is an exponential term. What is alpha? I am not going to specify, but this alpha must be such that this whole thing is dimensionless. A is once again the normalization constant, which ensures that if I integrate over minus infinity to plus infinity, I get unity. Now, if you calculate Vx average, you look at this mathematical form. This is Vx square, which says that probability that Vx has a positive value or negative value. Let us say Vx is plus 5 with appropriate unit or Vx is minus 5 the probability will be the same. That means it is equally probable to have positive velocity and negative velocity of the same magnitude. So, Vx average from this argument immediately is equal to 0. So, mean velocity is not very helpful for us. We should go for something more. We will talk about something called RMS velocities. Now, there is one more concept which turned out to be very useful, okay? That is called speed distribution. Define speed which is root over Vx square Vy square plus Vz square, and define a probability distribution Pv dV some normalization constant B V square E again A V square dV. So, this asks the question, what is the probability that speed of a molecule lies between V to V plus dV. So, speed lies between V to V plus dV. Okay. You see there is a V square term here in comparison to this distribution I have talked here. So, this makes a lot of difference. One can talk about a mean speed, one can talk about a most probable speed, but those are the things I am not going to introduce here. What I tried to harp on you, emphasize here, that there is a distribution. Even if you talk about molecular level, you are dealing with a huge number of molecules, you have to have some distribution function. This is the velocity distribution function for Vx. Similar form will appear for Vy and Vz because of the isotropy. Then more important to look at the speed distribution, where speed is defined like this, and this is the probability that speed of a molecule lies between V to V plus dV. Okay. Having said this, let me erase whatever distributions I have discussed, but please remember that whatever we will be deriving in the next part of the lecture will be connected to these distributions. We will talk about some RMS speed which is an average quantity, and having emphasized once again on the importance of the probability and probability distributions, let us talk about ideal gas. Quick recapitulation, that an ideal gas, I said it is a limiting situation of a real gas, limiting situation of real gas at high temperature and low density limit of real gas, limit of real gas. Okay. This is your ideal gas and it is a high T and low density limit of real gas. Now, I told you briefly also about the laws of ideal gas, which experimentally one can verify with a real gas at low density and high temperature. Firstly, I talked about Boyle's law, PV is equal to constant given T is constant. Then for a given volume of gas, you can say pressure is proportional to T, which is one form of Charles's law. Okay. This T I defined as the absolute scale, Soon the physical implication of this absolute scale will be clear. I said absolute scale is T Celsius plus 273.16, let us say roughly 270 degree Celsius. This is your absolute scale. Now, these are the equations. This is Boyle's law, this is Charles's law, proportional to T. Taken everything together, I can say in equilibrium, again remember
that whole study we are doing here, okay, is based on the concept of equilibrium. That means I have reached a state where none of my measurable quantities depend on time. If you like to see things in the microscopic level, I would say that distribution absolutely does not depend on time. So, now PV is equal to nRT, this is the ideal gas constant, this is the number of moles, okay. This is the ideal gas equation. Actually, this ideal gas equation helps us in establishing the absolute scale. If you skip V constant, as I said in my last lecture, if you keep V constant and plot P as a function of T, you will find a linear plot, because P is proportional to T, but there will be deviation if you go lower and lower in temperature. I told you low temperature, that means some length scale which I call the de Broglie wavelength will shoot up because it is root over of kT. But one thing we can see from here, that if I go up to T is equal to 0, rather if we could go up to T is equal to 0, pressure vanishes, okay. That is my absolute 0, okay. So, T is equal to 0, I will refer to as absolute 0, okay. Now, what is the advantage of choosing ideal gas? It does not, this scale does not care whether I am using a mercury thermometer, a clinical thermometer, whether I am using a thermocouple, it gives me a universal description. This is important, that I am giving a universal distribution to my temperature scale. This is first. Secondly, T, practical purpose, it is very useful, T is always positive, and T is equal to 0 is something which I can never attain, okay. You will later see when I go to Carnot engine, that if I could reach T is equal to 0, then Carnot engine efficiency will go to unity, which is never possible, okay. So, it is not that because I do not have a proper thermometer, I cannot reach T is equal to 0, it is a law of nature. Nature enforces on me that I can never reach T is equal to 0, and later I may tell you that there is something related with entropy. If I discuss about entropy a bit, I will tell you what is the implication of T is equal to 0 on entropy, okay. I succinctly summarized whatever we have done so far. Please remember these concepts at the back of your mind when we go to the next step. Let us consider first an ideal gas. I tell you the purpose. I will do a microscopic approach to arrive at something macroscopic. So, I will take a microscopic approach to arrive at something macroscopic. That means, I will try to arrive at pressure given in terms of microscopic variables in a average sense, okay. Now, ideal gas confined in a volume V, this volume I choose to be a cube. Well, it need not be a cube, it could be a sphere also. This whole calculation goes through, but mathematics will be slightly more complicated. You will need a different coordinate system which you will learn later, which is called spherical polar coordinate system. So, but for the simplicity, I will use a cube which is L cube, okay. 3 edges of the cube each given by L. So, this is my container, and this is my cube within which gas particles are moving in every direction randomly, and let us say I have a velocity axis which is Vx, Vy and Vz if you like. So, let us take a particular individual molecule which is denoted by I. Okay? Let me call it I and two faces. Two faces. Well, two faces of the cube, let us say these are yz plane in the velocity and this is the component Vx. I call it Vix, which is ith particle x component of velocities, and this is going normally, hitting normally these two faces which are yz perpendicular to the direction of velocity. You know, and what we will calculate? That I want to calculate pressure. So, what I will calculate is momentum transferred. What I will use to calculate this momentum transfer? Okay, I will use elastic collision, and of course, as I said, everything will be done in the framework of Newton's laws. So, I will do everything within the framework of Newton's laws. Now, this fellow Mi goes and hits this face of the cube, let me call it A1, let me call it A2, it goes and it gets elastically collided and it comes back. We know from the momentum conservation, we can immediately see what is the momentum change of ith particle. Of ith particle, that I can immediately write, it is Mi, let us say Mi, okay, and Vix, this was the, if say final, or I can say this is the final, and initially it was moving with Mi Vix, okay, or both negative, it should be subtracted. This is the final, this is initial, I am subtracting one from the other. Now, I assume, which is very reasonable to assume, that I will call all of them having mass m, and also sometimes I will need soon that it is monoatomic. So, I write it a monoatomic ideal gas. So, this is the net change of momentum, this is the magnitude in change in the momentum, magnitude in change in momentum, okay, in change in momentum. It's just this quantity, okay, this is just this quantity. So, this much momentum has been transferred also to the wall, right. So, particle number I, change in momentum of the particle number I is this, and this amount of momenta has been transferred to this A1 phase. Now, this is single collision. What will happen to this particle now? I assume extreme dilute limit, okay. I assume extreme dilute limit. When I talk about dilute limit, I assume that this particle goes and hits here and comes back here without any collision. This I can approximate only when there is something called mean free path. I will explain to you very soon in couple of lectures what is a mean free path. Okay? Mean free path is the average distance. Again, I emphasize whatever we are talking about here is in terms of averages. So, we emphasize that there is an average distance for a particle between two successive collisions. Between two successive collisions, a particle will face no force, eventually it will have a linear motion, okay, before it hits another particle, and if this mean free path is very, very large, I can assume that this particular guy is not having any further collision coming back and hitting the wall. And same story happens, his Vix is same, it keeps traversing between these two walls. But remember, it is an elastic collision, there is no change in velocity. Okay? So, it simply keeps bouncing between these two walls with a velocity Vix. So, you can ask me then, what is the number of time, what is the net number, what is the net number or of hit this fellow will make on this. Okay? You can ask me the question, okay, how many times does it hit over a time interval, let us say delta t. If I call there is a time interval delta t, and remember the velocity remains the same throughout, it is Vi x component I am interested in. So, it is Vix. So, delta t between two collisions. Okay. Let us write it in the way 2L is the total distance, this is L, it has to hit here, it comes back, goes back, total distance is covered between two hittings to the wall A1 is actually 2L. Vix is the velocity of that particle, x component of the velocity. So, this is the delta t time. Okay. So, this is delta t, and how many collisions per unit time? If someone asks you per unit time, how many collisions I will be having? I will be having a collision which is n 1 by delta t. Okay. Delta t is time for one collision. This is the number of collision per unit time. So, it should be 1 over this, and that will be, if I put it, Vix over 2L. Okay. We already have seen what is the total momentum transferred. Total momentum transferred at each collision is 2m Vix, and per unit time, okay, how many collisions are there concentrating on a particular phase E1, that is given by this number. So, total momentum transfer per unit time, if I may erase this part, let that figure be there for some time, other part. So, I just use half of it. So, I calculate total momentum transferred in per unit time is simply given by, let us say, delta f n times 2m Vix, 2m Vix. We have calculated what is n, I can substitute it as Vix over 2L. See, n is an arbitrary number, delta t is an arbitrary number which never appear. All that appears mass, length, these two we already know, and Vix which we really do not know, but we can talk about it in an average sense. Okay. So, this 2m Vix, so that takes care of the V I was talking about, and then I can calculate for all molecules. Let us 2 cancels out m. So, sorry, this 2 cancels out with this 2, I can forget about this 2, this is what the total momentum transfer per unit time. Now, I have considered only one molecule. Okay. Now, for one molecule, this is the momentum transfer. I am dealing with many molecules, number of molecules is of the order of the Avogadro number. So, I have to average all these molecules. I am assuming they are non-interacting, all these molecules on an average hits this boundary and providing momentum transfer here, causing momentum transfer here. Okay. So, now what is F? total momentum transfer per unit time. Here, due to molecule I, let me complement it, and total momentum transfer for all such i's will be given by ml sum over I vi xi square. This is the net momentum transfer. Okay. Now, this is very important concept. You see, if I have a distribution and I divide it by a quantity n, I will come back to this issue. Okay. I just multiplied upstairs and downstairs by a factor of capital M. So, I am finding out a quantity which is like a mean. You can see, take first particle, x components of its velocity, square it and then add them, divide by this n. This has a very important significance. I told you the velocity distribution is of this form, that velocity, average velocity of x component should be is equal to 0, because probability is same for any plus Vx and any minus Vx. Since plus Vx and minus Vx are equally probable, mean value should always be 0. If you take a coin and flip it many times, you know probability of up is half, probability of down is also half. If I assign a number, up means plus 1, down means minus 1, on an average I will get a 0. So, velocity is 0, but that does not stop, mean velocity, average velocity is 0, but that does not stop us from coming to an equation involving mean, which is the mean of the square. So, one more thing I just now will do that. We have come to this point. Now, I will use something which I have been harping on from the beginning, isotropy. What do I mean by isotropy? I mean that Vi x square average or sum over this should be equal to Vi y square average should be equal to Vy z square and sum over I. And you can, if you divide everywhere by n, this n, you can have same average value. So, all I wanted to say is from the beginning that Vx, Vy, Vz, there is nothing to distinguish between them. Okay. I am now going to use this formula for the next thing. Since these three are equal, I can always write whatever I wrote as Vi x square, okay, sum over I is equal to 1/3 sum over I Vi x square Vi y square Vy z square. Okay. All I have used, I have added same thing 3 times and divided by a factor of 3. Okay. I divided by a factor of 3 and then I am going to use it here to arrive at so called momentum transfer, and from this momentum transfer I will go to the expression of pressure. So, we reached up to this point that Vi x square is 1/3 average of these 3 quantities. So, what I am doing, I am adding 3 same thing and dividing by a factor of 1/3. So, I am getting the same result, but it gives me the whole picture of the space. If you remember, which I erased, we started with a cube. Okay. So, and particles can move with equal probability in any of the directions. So, we should have a net average sense. So, total momentum transfer, if I now allow to write, is I can write it simply in terms of 1/3 m divided by L, if you like, Vi vector square. Just telling you that I have taken the consideration all the components of velocities x, y and z, where Vi vector, it is nothing but Vi x square plus Vi y square plus Vi z square for the ith particle. But remember, what I am getting is essentially average, because I am adding over all the particles which are there in the container. Okay. So, now to give you the more better sense of average, what I can do, this is, remember, I have been telling, this is the net momentum transferred to the wall by all the particles those I am considering. So, total net momentum transfer is this quantity, and now I can have a sense of average. How do I do that? Let me write it, L outside 1 over m summation over I to n Vi square. Okay. Vi dot Vi, I can write simply it as a scalar, as long as we remember that it is just Vi dot Vi, as long as remember this is a scalar quantity. Now you see its speed. Okay. Now you see this is a average quantity. Okay. You are adding the speed, if you like, of each particle, squares of this, take speed, square it, add them and divide by the number of particles. So, what it is giving me? It gives me mean square. Mean square. Okay. First I square, that I take the mean, I add them and take the mean. This is the mean square velocity. I will go further. I will call this whole thing as Vrms square. Okay. So, what is Vrms square? It is this quantity. Square root of this is Vrms. I told you, so Vx average is 0. I will talk about RMS velocities. So, what is RMS? Mean square root. First we are squaring, taking the mean and square root, that defines as Vrms for us. So, I can write this entire thing as MNL Vrms square. So, you see this RMS has the information that I have n particles in my container, okay, and it has the information about the average I have been talking about. I cannot simply talk about a particular individual molecule, rather I can talk about average, and this is reflected here. So far I am dealing with things which are very esoteric in some sense, because who calculates momentum transfer? Nobody calculates in their laboratory what is momentum transfer. Nobody calculates RMS velocity in that sense. Okay. So, what do we calculate? We calculate the pressure, that we can always calculate. So, whatever I have derived so far should be related to whatever related to measurable quantities, that is called pressure. Let us do it in the following way. Okay. Let us try to calculate pressure. Pressure, we know, momentum transferred per unit time, that gives me the force, and then dP dt is equal to force, if you like, and divided by the area you are considering. We took a cube. So, this area was L square, this area was L square, this is the pressure, and this is the pressure we experimentally measure. So, this is pressure. Now, I have expression for this F. I know what is pressure. Pressure is 1/3 m n over L, okay. Well, m n over L divided by L square and then V RMS square. This is my pressure. This is my expression of pressure. And now see, we have come to something very interesting. M into N divided by L cube. L cube is the volume of the container. What is small m times capital N? That gives me the total mass. So, I immediately know pressure is 1/3 of rho V RMSS square. Okay. So, this is how VRMS, if you like, is related to macroscopically measurable quantity, that is pressure. Now, someone says, well, I want to write my PV equation, because you know, for an ideal gas we have been constantly saying if temperature is constant, then this thing should be related to PV is equal to constant. I am dealing with an ideal gas, so I should get a situation in which my Boyle's law holds true. So, PV is equal to then 1/3 into rho, 1/3 into rho, but I am multiplying rho times the volume, that gives me the mass and that gives me the VRMS square. So, if you like, this is your pressure derived from completely microscopic approach. In an average microscopic approach, this is my pressure, or I can write it further. This is mn VRMS square. Okay? So, this is the expression of pressure. After all this work, we have related an equation involving the pressure and volume, and we know for an ideal gas this quantity is related to temperature, right. PV is equal to nKT if you like, or nRT if I have n moles of systems. Let us talk about 1 mole and let us see whether I can talk about this PV equation. Okay. Let us first assume that, then I will try to explain it more details, that how this concept of temperature comes into business. So, microscopically we have found out some expression of PV. Question I am asking, is this PV related to temperature some way or the other, and this is what I am going to do in this few minutes. So, now let us consider 1 mole of ideal gas, then we know PV is nothing but n kBT or RT. Here n is the Avogadro number, here is the n kB is the Boltzmann constant. So, immediately you see that if I accept both of them together, so what we have found out? We have found out 1/3 m n VRMS square is actually PV. So, what happens here? Simply you can see temperature is related to this. I can simply write out half m VRMS square is equal to 1/3 m VRMS square is nothing but kBT. So, if you define absolute scale temperature, this is how you get to your form of temperature. So, what is temperature? Temperature is related to whatever you talk about. Temperature is related to the RMS velocities, okay. But we can go further, okay. If I say that total translational kinetic energy molecule, okay, a single molecule. Remember, though I am talking about single molecule, the RMS gives you already the sense of average, okay. This quantity is simply given by 3/2 kBT, okay, you see. So, total translational kinetic energy of the molecule is given by the temperature. So, what is the definition of temperature in kinetic theory? You will simply say it is nothing but total translational kinetic energy of the molecule that I am considering. Okay. Now, I can go further. I can use this to derive something which is fundamentally more important. Let us see what did I arrive at so far. I have got PV is equal to 1/3 m n V RMSS square, okay, and then I have found out half mv RMSS square is equal to kVt. These are the two important things we have gotten so far. So, you see it is 3/2. Okay. Now, you can ask, I can ask you the question that can I go further? Remember, I am talking about total translational energy, total translational kinetic energy. Firstly, why kinetic? Kinetic. Why kinetic? Why kinetic? Because there is no interaction, there is no potential part, there is no potential contribution to the energy, it has to be all kinetic. Why translational? Why translational? Because I am assuming monoatomic, okay, monoatomic, okay. There could be other degrees of freedom. These molecules I am assuming monoatomic and they can only translate, okay. That is why this is a translational kinetic energy. But you know there is one form of kinetic energy also which is half I omega square, right. If I allow the molecules to have a rotation axis and rotate about that, then you have to take the total kinetic energy and appropriately add this number 3/2, okay. Now, why 3? You can ask me why it is so sacrosanct that you have 3 there, because I am talking about a 3-dimensional container. If I could have in, for example, imagine that you have a 6-dimensional container, this number 3 should be changed to 6, okay. So, the first question which might occur to your mind that why this is 3? Because I have a 3-dimensional container. Second question may come that why this 2? Okay. This 2 comes from the fact that you are assuming EP, energy of any particle with momentum p, is of the form p squared 2m. I told you, you are using Newton's laws. Okay. Now, very interesting situations can happen if you have relativistic gas. Some of you may know, or if you do not know, if you can look up, you will find out relativistic gases, if rest mass is 0, this is the relation between momentum and energy, and in that case you will not get a 2 here, rather you will get a 1 here. So, this is the significance of getting 3 here, 3 because it is dimensionality, or 2 because EP goes off p square over 2m. Okay. So, having said this, now I will put something more fundamental to it. Okay. Now, you have total translational. Let us say I am talking about ideal gas, I am talking about 3 dimensions. Now, immediately these two things, this is the total translational kinetic energy. Total translational kinetic energy will be given by half, okay, m capital N V RMSS square. Okay. Now, this quantity and this quantity, if you connect these two, you immediately have a relation PV is equal to 2/3 E. Okay. This is something I want to emphasize, because this is a very, very important relation. This is a very, very important relation in the sense PV is equal to NKT is typically for a classical ideal gas. That means you are working at a very high temperature and low density limit. Okay. But this PV is equal to 2/3 E, it is valid even at low temperature. If you go to your higher studies on thermal physics, you will see this is valid at very, very low temperature, When you know low temperature, you cannot throw away interactions. You are talking about atoms and molecules. These interactions are quantum mechanical nature. So, you cannot get rid of them. Even then, if it is ideal gas, that means only kinetic energy, no potential energy. Okay? Okay? To make things clear, I make it E translational. Only translational energy. Okay? You are in 3 dimension and single particle in some form you can write as p square over 2m, okay, maybe in operator form, but it is p square over 2m. This relation holds true. So, temperature is completely out of the problem. So, what we have learned so far? We have found out a connection between P, V given in terms of RMS velocities, okay, and then I recalled ideal gas. Okay. In the next lecture, I will not directly use this equation, rather I will try to emphasize physical arguments that this quantity should be equal to temperature. Now, once you have this, you have two fantastic relation. Pressure is given by this, okay, and PV is equal to NKT, total translational kinetic energy is given by this, PV is equal to 230. Now, having heard this much, if someone asks you what is so called temperature in your problem, temperature is given in terms of mean translational kinetic energy. Mean translational kinetic energy is given in terms of V RMS. Okay. So, we reached using PV is equal to NKT, we reached this, and I am now going to play a little bit with this expression mV RMS square is equal to 3 by KT, okay, and then things will be very easy for me. Okay. First, two limits of this I want to discuss before I go to tomorrow's lecture. Okay. I want to calculate two aspects of it and then I will wind up for the day. So, you see this is this, and again I said mean translational kinetic energy E total is given by 3 n by 2 kT. Okay. Experimentally you never measure energy. What do you measure is the response. What you measure is specific heat. So, how do you calculate specific heat from here? You can calculate specific heat just taking the derivative of this with temperature. So, what I am trying to calculate? I am calculate what is the change in total energy given that I have changed the temperature by small amount. This is what we experimentally can measure using calorimetry. You already know how calorimetry relates total heat contained. Remember, heat is an energy and we are talking about one more energy here, which is translational energy. Okay. So, heat being an energy, mechanical energy being an energy, they are transferable from one to other. So, this gives me this definition of specific heat E total. I will come back to this point, connection between this total energy and internal energy in thermodynamics, which is related to the heat directly when I tell you about first law of thermodynamics, okay, which is nothing but first law of thermodynamics is nothing but the conservation of energy. So, you do this, you get a relation which is this. Okay. This is the specific heat. You take many gas, do the experiment at high temperature, measure the specific heat. Okay. If you measure the specific heat, you find out this formula which immediately gives me 3 by 2 n kV. Okay. So, this is called Dulong-Petit's law. Okay. So, it has got a name, this is called Dulong-Petit. So, it follows immediately from this expression of the mean kinetic energy or total translational kinetic energy of the system. Second thing is fundamentally very important. I have found out half mv square, I will not write the word RMS any longer, is equal to 3 by 2 kT. Okay? But whenever I talk about V square, you should interpret that I am writing RMS square. Now you see that it has 3 contribution. Okay? Now you have already used that it has 3 contribution. If you like, I can think of only moving in one direction. Okay? I can think of this quantity as 3 half kts. 3 half kts. Okay? You see 3, 3, and I told you why there is this number 3 is coming, because I have 3 velocity components. My gas molecules can move in 3 direction. So, this immediately hints to me that what should be the quantity if I calculate m v x square average, because that must be equal to half m v y square average. Clear? It should be then necessarily m v z square average. So, in the average sense, these 3 things should be same. Okay? If these 3 things are same and total kinetic energy is 3 by 2 kT, I immediately conclude that half m v x square average is nothing but half kT. Okay? It is very, very important that each kinetic energy is half kT. I do not have any potential energy in the problem. So, half mvy square is equally would be half kT. So, each degrees of freedom contributes a half kT to the system. Okay? Each degrees of freedom gives you a half kT of the system. Now, this is very, very important. This is called equipartition of energy. Okay? So, this is called the equipartition of energy, which is very, very important for many aspects, and one of the aspects I already mentioned, that it goes to the specific heat. So, I think I will stop here today, and tomorrow I will recapitulate this ideal gas equation and do everything with a recap and take it beyond this ideal gas thing, and I will give the notion of mean free path, which I have not so far used. Thank you for today.